Alrighty, hey guys, can you hear me? Are there any questions before we get started on today's lecture? Any questions? If that's not the case, then could go with the Bernstein theorem. Yeah, we can talk a little bit about the Bernstein theorem. Okay, so we mentioned it briefly in class, but we didn't make a big deal out of it. It's because we didn't prove it. So first of all, let me just show you where you can find more about it. The theorem is here. It's this exercise 1.5.11. It's this Schroeder-Bernstein theorem. So let me try to write it down and talk about why it's important. So but we say that the cardinality of, say, A is bigger than or equal to the cardinality of B if there exists a map from A into B, which is onto. And then we also say that the cardinality of A is equal to the cardinality of B. Keep in mind, we're comparing there's a question from Aya. Is it true? Is it true the other way around? Aya, can you help me here? Which one do you want to turn the other way?
Can you hear me?
Yeah.
Yeah, if there is a function that is onto it, implies that the cardinality is larger or equal to cardinality of B.
Yeah.
So it's a if and only if statement.
Oh, so in definitions, you can only have if. Right. This is my definition. We say that the cardinality of A is bigger than B if there exists such a function.
Okay, but you don't write if and only if?
I don't, you will never see me write if and only if in definitions. If and only if,
okay.
if and only if, this is a bijection. And definitions are just, this thing here holds if something else is true. So you will never see me write this in definitions.
Yeah, but is it true that if there is a surjection, then cardinality is larger than cardinality of B?
Yes, that's correct, right? Because that's your if. You can say if here,
okay.
when.
Okay. All right, thank you.
So keep in mind, like this greater than or equal to sign here, this is not like the one that we have. This is not the one that we have in the real numbers. This is not an ordering on the real numbers. This is an ordering between infinities. So what does it mean to say that two things are the same? Right now we're putting equality signs between two infinities potentially. We say that these are equal if there exists a bijection. Which is both one-to-one and onto. Right, so the complication is that and this is this Schroeder-Bernstein theorem. What do we have? Well, do we have some sort of, do we have the usual property that if this holds and the opposite holds, then we have equality? Like we're used to saying that if A is less than B and B is less than A, well, then A and B are the same. So the Schroeder-Bernstein theorem says that if the cardinality of A is bigger than the cardinality of B, if the cardinalities have this property, right? So you can find this function. If this is true, so there exists a function that goes from A on to B. And so if this is true and that the cardinality of, well, B is bigger than the cardinality of A, right? So there exists another function, let's call it G, which is onto. Well, then there exists a new function H, which goes from A to B, which is both onto and one-to-one. Which is both one-to-one and onto. And now I switched the roles already, right? As we have, should not have A and B here, it should be switched around, it should be B and A. Right, so this is a Schroeder-Bernstein theorem. It says that, yes, this really works out this way, that this order that I have myself created through these surjections, that you have this property that if I can find one surjection and then I can also find another surjection, then you can miraculously combine these two things and you can get this one-to-one and onto function. This is the Schroeder-Bernstein theorem. And this is not easy. So how do you get from F and G, how do you create your H? And so that exercise, this was exercise 1.5.11. It's not going to be that. It is not going to be that easy, Priya. Unfortunately, it's not that easy. Brian is asking about a real group. I'm not sure what this is about. Brian, do you want to say something about what this group is about? Okay, I'm not sure what that is about, but GroupMe, real analysis. Maybe this is a place where students can interact. Did that help for Priya? Did that help on the Schroeder-Bernstein theorem? We won't prove this. This is taking us. This will take us too much time to do. Are there other questions about cardinality? Then we're going to shift gears, and we're going to move into chapter 2. Let me just show you chapter 2. So the first sections in chapter 1, we didn't spend too much time on the first sections in chapter 1. We did prove bits and pieces of the first one, so we spent quite some time on 1.5 and 1.6. And now we're going to move into chapter 2. And we're going to start. There's quite a bit of discussion here in the beginning, and I'm going to see if I can give you some sort of an overview of some of the things that he's trying to get at. But we're going to be spending a couple of lectures on doing this. And for example, we're going to get down to this Cauchy sequences down here, and we already had mentioned that this is one way to create. The real numbers. So one way to create this square root of 2 up there is through a Cauchy sequence. So there are lots of things in here that are very relevant for real analysis. And we're going to try to do a few examples that if we can wrap our heads around that, I think we can come a long way. And that being said, I'm going to be giving a few proofs throughout. We need to do proofs too. So we'll see how it goes. So what we're going to be talking about will be sequences. There'll be sequences and series. All right, so a sequence, let's start by saying what that is. A sequence is a bunch of numbers, an, there are infinitely many, the indexed by the naturals, and the, in our case, real numbers. All right, so there are many ways to write this. This would be typically how I write it, a, and then there's this subscript, and then n in the natural numbers. And series is a little bit different. These are sums, so you'll be summing these a's typically from 1 to say n of an, and then capital N here, this is a natural number. So these are finite sums. Right, this is a finite sum. Some people call this a partial sum. And then the difficult part here is we're going to be looking at these limits. So we're going to be looking at expressions of this type, n equals 1 to infinity of an. Right, so there is, over here when you talk about the natural numbers, so there is no a infinity, right? There's not such a concept. You need to use limits. Instead, we'll take limits of an. Same as here, this capital N here, there's no infinity inside n, right? Infinity here, this is not an element in the natural numbers. Right, so what is this thing here? Well, this thing here is going to be some sort of a limit of these finite sums we have over here. But this is going to be as capital N goes to infinity. Okay, so why is this a big deal? All right, so the problem in a nutshell with these guys over here, the problem in a nutshell, is the following. There is no way, and so no here, there is no way to define plus infinity minus infinity. This is a problem in a nutshell, right? So you might have come across, you've probably seen you probably seen situations where you would have stuff like f of x divided by g of x, and then g of x, for example, could this could approach 0 as, say, x goes to plus infinity. You've probably seen expressions like these ones before. And so then you would end up in a situation where some professors write this as like a 0 over 0 situation. And then what do you do? Well, then one thing you can do is you can try to use L'Hopital's rule. Does that seem vaguely familiar to some of you? So the problem here is, of course, that we can't define 0 over 0 in general. How do we define 0 over 0? We're not going to define this to be 1. It would never work. Right? Examples like, silly examples like, we're going to get too far straight. So we have seen situations where it is difficult, where you cannot define what does it mean to divide by 0. Well, you have to look at a limit in order to understand what the quantity goes to. And the same thing is true here. There's no way to do this. You can try, so you can have situations like, so you can define, so it's possible to define that if I take plus infinity and I subtract away, say, a natural number, then this here, you can define this to be plus infinity for any natural number. I can take 1,000,000 and I subtract 1,000,000 from plus infinity. This is still plus infinity. This is okay. And I can do the same thing. I can do the same thing with minus infinity. I can add any quantity that I want, and I'll just say that this is minus infinity. So this is okay. We cannot do this thing up here, and this is going to present an enormous amount of trouble for us. So keep this in mind. This is a fundamental problem in math. There is no way to define plus infinity minus infinity. I mean, this is to a large extent, like these cardinalities here, we don't start, like when you start ordering these infinities, it's tempting, right? You start moving a minus infinity over on the other side. So what is then the cardinality of A minus the cardinality of B? And I want you to be careful about this because these cardinalities, these are potentially very large quantities, and you can easily run into trouble. So this here is the problem in a nutshell. When it comes to studying these series that we have up here, and we're going to see some today that are nothing but trouble, and they come up from this issue here. Okay, so let's get started and look at some basic examples. So one example is take a sequence. I want to have my sequence just to be something very simple, 1 over n, and n is a natural number. So where does this go? Well, the claim is that the limit as n goes to infinity of an, what should it go to? Well, 1 over n, as n goes to infinity, this is going to go to 0. Right. So how does one check something like that? So what is the definition? What is the definition that we're using here to say that the limit is 0? Right. So this is because, and this is the definition. What does it mean to converge to 0? Right, so I'm hoping that in your 300 level course you have seen limits to some extent, but let me just recall what it is. It means that you take any epsilon, Then you can find a big number such that for any numbers that are even bigger, right? So give me an epsilon. Okay, so somebody hands you an epsilon. It's a small, however, strictly positive number. You can find a humongous natural number, such that when you come after that humongous natural number, what's going to happen is that this an in absolute value is very close to its limit. What does it mean to be very close? Well, you take the absolute value of the difference, and this is going to be less than that epsilon. Right, that's the definition of this sequence here converging to 0. And as you can see, it requires that you have a guess here for what this what this limit is. Right? That goes in here. Right? You're going to say that this limit is equal to 0 if this property here holds. And so why does it hold? Well, we need to check it. So how do we check that? Why does it hold? Well, so epsilon bigger than 0 is given. This is given to us. Our job is to create, so we need to create, and our job is to create this natural number with the property that an is small. Right, an minus 0 is still an. An here is also positive. This is 1 over n. Right, this here has to hold for any n that comes later than capital N. Okay, so how are we going to do that? There's no claim here about uniqueness, so we just have to find one capital N that will do it. Right? That just has to exist one. How will we do it? Well, we'll set this capital N here. It has to be a natural number, so we're going to set this capital N to be something specific, and the specific number I'm going to choose is going to be like basically solving here for epsilon. So I'll move n to the other side and then divide over. So I'll have 1 over epsilon, and then these funny brackets. Let me put an extra 1 here just to be sure. Right, so this is the smallest number, which is the smallest natural number which is bigger than or equal to 1 over epsilon plus 1. Right, and such a number exists, and this is this Archimedean property that we discussed last time. So if you're not used to these brackets here, let me just look at an example. So for example, if epsilon, say that epsilon is something specific, I picked, just picked a small number. Say epsilon is equal to 0.0003, which is a small number. Then 1 over epsilon, this is equal to 1 divided by, well, 0.0003. If I did this right, this is 3,333.33. Right, so in that case, the integer part above 1 over epsilon, this is going to be 3334. And this is a natural number. Okay, so now I'll go back to the general case. This is my natural number, and we just need to check now that this n here indeed works. So let's check that n being just 1 over epsilon plus 1, that it works. How will we do it? Well, we look at the difference. An minus the 0, this was equal to 1 over n. Well, 1 over n, this was going to be bigger than or equal to 1 over, so n was going to be bigger than capital N. So if I divide by 1 over n, dividing by a smaller number, I'm going to get something that is bigger. And if I divide by 1 over epsilon plus 1, I'm going to get a smaller number, right? Because n here was bigger than or equal to the number on the right-hand side. And then I can throw away the 1, and I'll get that this is less than epsilon. And the property then holds. It is really true that give me an epsilon, I can find a humongous big natural number such that when I come after it, I'm squeezed below epsilon. And therefore that limit up here is 0. But again, there's no natural number. There's no natural number here that will give me 0. No matter what natural number I stick in here, I will never get a 0, but the limit is 0. Any questions on this part? So one thing that one should not neglect, right? So to check this, you need to have a good guess. You need to guess. You need to guess that that the limit is really 0. Right? Because if I would have plugged a 1 in here, I would not have something. I would try to verify something that is not true. So you need to be good at guessing the limit and then go back and check it, right? So this is like a guess and check. It's like a guess and check procedure. So how would one go about doing this in a homework problem? Well, the way that I would go about doing this in a homework problem is use our fancy computer. And let me show you how one could go about doing this. Right, so I'm hoping everybody can see my Mathematica code here. It's not really relevant what's up there, it's just Scratch. Right, so if I were to look at a limit, so I'll write limit, and then I'll write 1 over n, that was my limit. And then I would have n, to infinity. But I'll ask Mathematica what it thinks that the limit should be. And Mathematica thinks that that limit should be 0. So that would be my guess. And then I mean, in this particular example, it's not so complicated, but it can get complicated. And you're welcome to use Mathematica to try to come up with guesses for what the limiting object is. And it's not complicated. I should tell you, though, that it's not always the case that Mathematica gets the correct limit, but very often it does. Any questions on this part? Okay, so this was an example, but we did go through the definition of a limit. Now we want to do series. I'll computer disappeared. Get this started again. Sometimes my document camera disappears, and if it happens and I don't see it, just let me know that it's black on your end. I'll try to get it going again. There we go. Okay, so the next thing we want to do is, now let's consider series. No, it's black again. Come on. Let me try this again. Try this again. All right, I'm hoping it's going to hold up this time. So the next thing we wanted to do was to consider the series, so the partial sums. So partial sums. So the partial sums for this particular example would be Sn. This would be the sum over the first capital N elements. And here, capital N, this is a natural number. Right, so what we're having here is you're having 1 plus a half plus a third plus a fourth plus all the way up to 1 over n. So there's no doubt this here is finite, right? This here is a number. In this particular case, it's a positive number. It's a positive number. So does it converge? Does Sn converge? In other words, do we have a limit? The limit as n goes to infinity of Sn. Well, so here we have a sequence of positive numbers, and okay, so if there is to be a limit, it's going to be from 0 up to and including infinity. So 0 included, and then up to and including infinity. It's not going to be a negative number if there is one. Another thing we can see here is yes, this is really true, because if I look at Sn, I'm going to get something which is less than or equal to Sn plus 1, right? Because the difference between these two terms is going to be the 1 over n plus 1 term. So we do have a limit. So this here means, so that inequality, yes, because we have monotonicity. Right, this the elements, each element inside the sum is positive, so this partial sum is increasing. And so we have a monotone sequence, and a monotone sequence has a limit. The price we're paying here is the price, or I should say potential problem with these monotone sequences is that they always have a limit, but the potential problem is that the limit as n goes to infinity of Sn, this element here, this might be something that could be plus infinity. This is possible. This is possible. So you have monotonicity. So there is you can be guaranteed that there's a limiting object, but what is unclear in this particular example is whether or not that limit that you get out is finite or if it's infinite. Right, so the theorem that we're going to be proving today is the following. So you're going to take a sequence. You're going to take a sequence of real numbers. So let this thing here be non-decreasing, like the one we have. So this means that an is less than an plus 1, and so on for any n. Then there are two things that can hold. Then there are two possibilities. The first possibility is that you converge to something finite. Okay, so when does that happen? The first possibility is that that the supremum over these ANs is finite. If this is true, well then the limit as n goes to infinity of an, this exists. Then this exists in R. The other possibility is B, that is that the supremum is plus infinity, else. So that means that the supremum over an, this is plus infinity. Either the supremum is finite or it's plus infinity. Well, then this limit over an is equal to plus infinity. And we haven't defined what it means for a limit to be plus infinity. So what does this mean? So what does that mean? What does it mean for a sequence to converge to plus infinity? Well, so here the definition is, it's not going to be the same as the one we had in the finite case. Right? In the finite case, you could get within an epsilon reach of the limiting point. Right? When the limiting point is plus infinity, you're not going to be able to get within an epsilon reach of plus infinity. So this here is not going to work. This is not going to work when you have infinity here instead. Right? An minus infinity, this is minus infinity. Take absolute value, this is plus infinity. Plus infinity is never going to be less than epsilon. This is not appropriate for a as a definition for a limit being plus infinity. So instead, the definition is you give me anything big for any huge constant. For any constant, I can find another constant such that for any little n bigger than that capital N, we will have that an gets above k. And that's what it means to converge to plus infinity. Our textbook, so I should just make a note here. Abbott, he doesn't like convergence to plus infinity. He doesn't talk about it at all. This is a great shame because it comes up, and there's nothing wrong with converging to plus infinity. So for us, we are in this course, we are allowed to converge to plus infinity, and the definition is this one. So what do we have here? Okay, so we have a theorem that says that if you are monotone, so here we're just looking at the increasing case, there are only two possibilities. An increasing sequence of real numbers, there are two possibilities for it. It's either going to converge to a finite number, or it's going to converge to plus infinity. Of course, there's a perfect analog of being decreasing, it's going to have the same properties, then you're just not going to converge to plus infinity, then you're going to converge to minus infinity. And you get one from the other simply by plugging in a minus sign in front. So here I'm just stating the non-decreasing one. So I want to take this theorem, we're going to prove it at some point. If we have time, we'll do it today. But before we prove it, I want to see what do we have here? We have that 1 over n goes to 0, and then I'm looking at these partial sums. These partial sums has exactly this monotonicity property. It increases as we have more and more terms in the partial sum. But what's the limit? So do we have a limit? So now we know that the answer is yes by this theorem. So is the limit finite? Does anybody have any questions or guesses on whether this limit is finite, infinite? Priya says it's finite. If it's finite, then it should then we should have a value for it. So if it's finite, then we're going to go with this definition, right? So to check this definition, you need to come up with a good guess to plug in here, and then try to prove that when I write Sn here, I subtract away this guess of that limit. Check to see if they can prove this. And it is true, right? The numbers that you add, they're going to get smaller and smaller and smaller and smaller and smaller and smaller. The problem is that you're adding more and more terms. So you have it's true that the terms that I add, they're not very big, they get smaller, but I also do add more of them. Okay, so when I was preparing the lecture, I was just looking around Google to see what do other professors do in what do the other professors do in for a course like for this example here, and let me just show you what one thing that came up. So let me share this file. So here's a file that says this is the series that we look at. This is, yeah, that's the series we're looking at. Like we add 1 over n, and so on. This is one of the most celebrated infinite series in mathematics. Okie dokie. What does he say? And he's going on to giving proof 1, proof 2, proof 3, proof 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. He's proving 20 different ways. He's proving 20 different ways that this series here converges to plus infinity. 20 different ways. I am not going to show you 20 different proofs of why this converges to plus infinity. I'm just going to show you one. But what this shows is you can see how far back it stretches, like 1350. This is quite a bit of years ago. This is an old thing, and I want to show you one proof of why this thing goes to plus infinity, right? So the claim is if I take the limit as n goes to infinity of this sum, that limiting object, this is equal to plus infinity. And this here is despite 1 over n despite that the tail terms d is small. Okay, so so how do we prove the claim? So we pick one of the 20 proofs in the document we just looked at. So here's one. We will write, you will write Sn. I'll write out the first term. So this was 1, put some space in between here, and then a half, and then a third, up to 1 over n, and then I exponentiate. Right, and the exponential of a sum is just a product, so I'll put exponentials everywhere here. Right, and then the pluses, they are not pluses anymore, they become exponential, they become multiplications, right? So this is multiplicative. Okay. So I did nothing else and just apply the exponential function. So here comes the first trick. I'm hoping that we have all seen and worked with the exponential function. So make a little picture of it. Make a little picture of the exponential function. So the exponential function is looking something like this. This is e to the x. And what I can do is I can put a straight line in here. This straight line here is, well, is 1, and then the slope is 1. So I have that e of x dominates this term for any x in the real line. And so what I do now is I apply this inequality to each individual term. This inequality here will imply that Sn is bounded from below. Well, the first one will be e to 1, so that'll be 1 plus 1. So that'll be 1 plus 1. And the next one, this will be, well, it'll be 1 plus a half. And then it'll be 1 plus a third. All the way down to the end. 1 plus 1 over n. And then what I can do is I can group them. These two terms here, that becomes a 2. And these two terms here, that becomes 3 divided by 2. And these two terms here, they become what? 4 divided by 3. All the way up to the very end, this term here becomes n plus 1 divided by n. And now the miraculous thing that we see is that this 2 and that 2 will cancel. And then that 3 and that 3 will cancel. And it will keep canceling like this. And I'll be stuck with this n plus 1. This is my last term. So I get that this exponential of Sn, this is bounded from below by n plus 1. Okay, so then what I do is I apply log to get Sn back. So Sn, like log is an increasing function, so I'll apply log. I'm not going to disturb the inequality. I'm going to get that Sn is bigger than log over n plus 1. And what happens with log of n plus 1 when n goes to infinity? Well, we look at the log function. It looks like this. Where does log go as the input goes to plus infinity? Well, this thing here, that converges to plus infinity. If I look at the limit as n goes to infinity of log n plus 1, this is plus infinity. And then we have the inequality. So 1 over n is big. Any questions on this? The sum of 1 over n goes to plus infinity. Can you explain how we got 1 over n again? Yes, I can. Let's go through it one more time. Like the first thing I did was I just wrote out what Sn was. Sn is the sum of these terms here, and then I exponentiated, and I just used that the exponential of a sum is equal to the product of the exponentials. Then I'm now going to use a bound on each one of these. Like I'm going to bound this term from below, this term from below, this term from below, and this term from below. And the way I'm going to do it is when we're going to use this exponential inequality. It says that the exponential function is it dominates this straight line here at that has the intercept of 1 and slope of 1. And so what I do is I apply this bound here to each of these terms. So the first term, I have a 1 here. So I'm looking at ex, x is equal to 1. So I'm going to get 1 plus 1 here. The next term, this is e to a half. So x is a half. So I get 1 plus a half. That's this term. The third term is e to the third. Okay, so x is equal to a third. It's 1 plus a third. It's that term. And it goes all the way up to the last one. The last one, x is equal to 1 over n. X is equal to 1 over n. So I get 1 plus 1 over n. This is this term. Okay, so now I have a product. And the only thing I'm going to do is I'm just going to recognize that this has this curious property that when I multiply them together, it simplifies. So this is a 2, and this here is 3 divided by 2. Right, so when I take 2 times 3 divided by 2, I'm going to get a 3. The next term, this is 4 divided by 3 times 3. 3 and 3 cancels out. I'm left with 4. The next term is 1 plus 1 over 4. That's going to be 5 divided by 4 times 4. This is a 5. They keep canceling out, and I'm just stuck ultimately with the last term, which is n plus 1. And that's the one I copied down here. So what we see is we have this property here that it is true that 1 over n converges to 0, but the sum diverges. So to get something interesting, what one could do is we could make it go faster. So try to make an go faster to 0. It's too slow. It picks up this log property. So try to make an go faster to 0. Any ideas on how we're going to make that work? Right, we had 1 over n. What could we do instead? This doesn't go fast enough to 0. What could I change? 1 over n squared. Awesome, right? This is still going to go to 0. This thing here still converges to 0. The limit here still converges to 0. But what about the sum this time? What does he converge to? Right. Keep in mind it's monotone. It's monotone, right? Because the terms in here, they're all positive. So the more I include, this is write this out so we can read it. The limit as n goes to infinity So what does this converge to? What is this limit? Well, now it's going to go faster, and now we're stuck in this situation. I don't know what the limit is. So how do I prove anything? So go back, give it a shot. Over here in Mathematica, let's see if we can get Mathematica to help us out. So what I'm interested in is a sum, right? I'm interested in a sum over 1 over n squared. I'll be summing from 1 to infinity. Like what I was doing before, let me just show you. What I was doing before was I was summing 1 over n. That was the one we just did. And you can see Mathematica doesn't like it. It says it doesn't converge. And that's like Abbott. He doesn't like to say that it converges to plus infinity. I'm a bit more liberal there. I'm okay with converging up to plus infinity. So 1 over n summed up to infinity, it doesn't converge to something finite, and Mathematica doesn't like it. But what happens if we squared it? So it's going to go faster now. This was a great suggestion. Let's try to do that. So if I hit enter here, I'm going to get my guess. And the answer that comes out is pi squared divided by 6. Okay, pi squared divided by 6. So you see, it's not so easy to guess these things on your own. This here is a guess from Mathematica. So how would one prove that? Yeah, so you start Googling. This is what I did. Is there an easy way to figure this out? And I knew of this problem from whenever back in the day when I took real analysis. And it is not so easy to figure this out, but it is possible to figure it out. So here's a little set of slides. It's called the Basel problem. And again, this is an old thing. Here's the date that is being listed is from the 1600s, right? And it's this sum where you square. And now we will flip down to see if he has the right formula, if it's the same as what Mathematica is listing. And you see there's something here, like it's pi squared divided by 6. And how would one go about doing it? And there's a nice proof towards the end. There's this proof that came out in 1983, which is this is easier to digest. And the way that he does it is by rewriting it in terms of a double integral. And then he takes you through how to do it. You're going to end up with this sum that we were interested in, 1 over n squared, and you recognize it as a double integral, and then you calculate this double integral. Okay. I just wanted to give you an idea about that it is possible to prove something like this is true. This one here is not obvious. So if you're interested in it, I'll give you the correct thing to Google. This is called the Basel problem. Are there any questions about this one? So the message that you should take away from this is that it is perfectly possible. It's perfectly possible to have a sequence that goes to 0. And when you sum it up, you're going to get plus infinity. You need the tail to go to 0 sufficiently fast. And 1 over n doesn't do that. 1 over n squared does. So now we talked about convergence of a sequence of numbers, and we talked about it converging to a real number. We talked about converging it to plus infinity. I also want to talk about divergence, because you might get this impression that when I take a sequence, I always have a limit, and I don't want you to have that impression. It's not true that you can just take a limit as yeah. So let's switch gears a little bit, and then try to see examples where this does not work very well. So divergence. Like we had convergence, right? We also have something called divergence. We also have divergence. This is when when this object here and does not exist. It doesn't exist in our broad sense. We are allowing for plus and minus infinity. And an example of such a thing is not too hard. If I take an to be minus 1 to the power n, and this is n is a natural number as before. I take this guy, and then I would have a1. This is equal to minus 1. I'll have a2 is equal to 1. I'll have a3 is equal to minus 1. I'll have a4 is equal to 1, and they keep oscillating between minus 1 and 1. So in this case, you are not allowed to write. You cannot write the limit of these ANs, because there is not such a thing. And this is what divergence is about. And so it becomes quickly a mess, because before you apply this limit operator, you need to know that there is such a limit. And so we cannot just blindly write this. And so instead, and this is it's a bit unfortunate that Abbott, he has put this stuff here over in an exercise, but please do have a look at this exercise 247. Instead, you should use these, not limits, but you should use these lim_sup over n to infinity and lim_nth. So let me talk a little bit about them. So we have lim_sup and we have lim_nth. They look a lot like lim. There's just a sup and an nth put after here. Right, so how are these defined? So for a sequence, so for this collection of real numbers, we define so lim_sup. There are a couple of ways to write it. You can write it like this and then put a line over it. Lim_sup. This is just the same as writing it out the long way. Also put it like that. So lim_sup, how is it defined of these ANs? Well, the way that this is defined, this quantity, whether you write it as lim with a bar on top or you write it as lim_sup, the way that this object here is defined is you take the limit as n goes to infinity, and then you take the supremum over k's that are bigger than n of ak. That's the lim_sup. And now there's a limit here, so we have to be careful. But what saves us is this monotonicity property that we had already used before. And here it's okay to write that limit, because we note that if I take the supremum, over k bigger than n of ak, and I compare it to taking the supremum, it's the n variable I'm sending off to infinity. Here I take it over k's that are bigger than n plus 1. If I compare these two suprema, here there is more flexibility. right? Because I can choose k to be n, I can choose k to be n plus 1, and so on. Over here, there's less flexibility because I cannot choose k to be n. So this supremum on the left is going to be bigger than or equal to the supremum on the right. So what that shows is that you have monotonicity. This is a non-increasing function. This is a non-increasing sequence. This quantity here, indexed by n, this is non-increasing. If I can write it, this is non-increasing in n, and therefore it has a limit. We have monotonicity, it has a limit. This was lim sub. You can also do lim inf. So if you write lim inf, you can put a bar underneath it. Lots of people do that when you write papers and books. Lim inf, you can also write it out the long way. And then you put an a in here. How is this defined? Well, again, it's going to be limit. And then you send n to infinity. But instead of supremum, you put now infimum. And you put k bigger than n of these ans. And just as before, the thing that saves the day is because you have monotonicity. So let's note that again. Let's note that again, that if I look at the infimum over k bigger than n of a k, just use a k, of ak, how does it compare to the infimum over ak, but now k is bigger than or equal to n plus 1? Well, here it's different, right? Because I have, again, more flexibility, and I'm trying to minimize. So I have more flexibility on the left than I have on the right. I'm going to get that inequality. So what we're getting here is that this is non-decreasing. This is non-decreasing. And it has a limit. And therefore it's okay. These quantities, they always exist. So I know most of you have not seen lim sub before, so maybe we should try a few examples. If we would look at our friend from before, this is 1 over n. We'll look at our friend from before, 1 over n. So if I am to look at lim sub, I'll need to compute the supremum k bigger than n of 1 over k. How big does this thing here get? Well, the bigger I make k, the smaller it gets. This supremum here, this is equal to 1 over n. So then the limit, the lim sub over the supremum, this is the lim sub over 1 over n, this is equal to the limit of 1 over n, and that's my 0. Likewise, if I computed the lim inf, then I would have to first compute the infimum, k bigger than n of 1 over k. How small can I get this? How small can I make this number? Well, I can make this number arbitrarily close to 0. The infimum is a 0. And so if I take lim inf this time of 1 over n, this is the same as computing the limit as n goes to infinity of a 0, but that's equal to 0. So in this particular case, lim sub and lim inf, they coincide, they both equal to 0. So lim inf of an in this case is the same thing as lim sub over an, and the limit exists. And this limit, it exists, and it happens to be exactly the same as these two. So we can go back to our first example where we did have a limit, and we can compute lim sup and lim inf in that particular example, we can see that they coincide, and they coincide furthermore with that limit. So now we go back to the trouble case. This is the one where we don't have a limit. This is this minus 1 over n. What happens here? Let's do the other example, and let's see the difference. We go back to the trouble case. This was an minus 1 to the nth. So here there's no limit. Okay, so let's see what happens with lim sup and lim inf. The first order of business would be to compute the supremum k bigger than n of minus 1 to the power k. What will I get here? What would I get here? It depends on if n is odd or even. Well, so n is arbitrary, k is something that is bigger than n. So k is, like this here is the same thing as saying the supremum over Rutgers is bigger than n of minus 1 to the power of Rutgers. Right, k doesn't have a meaning here. K is just a variable I use to describe the problem. What will I get for the supremum? That's right, I'm going to get 1. So then I'll take the limit. I'll take the lim sup over minus 1 over minus 1 to the power n. This is equal to the limit as n goes to infinity of a bunch of 1s. This is a 1. Okay, so now I do the infimum of minus 1 to the power k. What do I get here? That's right, this is minus 1. So then I'll do the limit, lim inf over n, minus 1 to the power n. This is equal to the limit as n goes to infinity of minus 1 over, of minus 1. So this is minus 1. And we see that they're different. Right. So lim sup of an, and this is strictly bigger than lim inf, and there's no limit. So you always have a lim sup, you always have a lim inf, but they could be different. And when they're different, there's no limit. Any questions on this part? So we only have a few minutes left. So here's a real troublemaker. So this is going to come next time. Next time is trouble. Next time is trouble galore. Next time is trouble galore. It is this guy here. We're going to be summing up. We're going to be summing up this minus 1 to the power n divided by n. Next time there's trouble. Does he converge? Does he converge? Is there a limit? Does this converge? So note here that it alternates. So there's no monotonicity. Of course, what we could do is, some of you might not be used to this way of doing math, but what we could do is get some feeling for this. What does Mathematica say? What does Mathematica say? What does he say to this thing? He was helpful before. Maybe Mathematica is going to be helpful down here too. What happens if I do -1 over n to the power n divided by n? What do I get? Okay, Mathematica says it's minus log 2. Okay, so Mathematica says the limit is equal to minus log 2. And I'm saying there's trouble in paradise. This is not so easy. And the reason that it's not so easy, it goes back to the very first warning I came with. What we should be really careful about here is plus and minus infinity. We cannot subtract them. I write that somewhere, so I have it on a piece of paper. This goes back. This example here is one of these bad ones. This here, underneath this example, we have this situation here. But we're out of time, so where we're going to pick up next time? Is going to be on this example where we have 1 over n minus 1 to the power n divided by n. We have this non-monotone series, and we want to study it. And we're going to get into a whole bunch of problems because of this this feature here. And then I owe you a proof of this fact that monotone sequences they have limits. So this here was just the beginning of this chapter. It was to look at some examples so you get a sense of what it is that we are facing. Are there any questions? We are out of time, more or less. Are there any questions before we?
So, Professor, in this scenario, like the last one, then the argument about the neighborhood around 0 wouldn't work?
Yeah. Yeah. So in the last one here with the log 2, where did my I end up going? What's this one here? So this is correct. This thing here, this does converge to minus log 2.
Mm-hmm.
So I do not believe that Mathematica is wrong. But there is a lot more to the story than that. Because you know that if I eliminated the -1 here, then you're going to be dealing with an infinite series. Right? Then this would converge to plus infinity.
Mm-hmm.
And so so inside here, there'll be positive numbers and there'll be negative numbers. It oscillates between those. And what do you think you get if you add up all the positive numbers?
Oh, I see.
And what do you think you get when you add up all the negative numbers?
Mm-hmm.
You're going to get plus infinity for all the positive numbers, and you're going to get minus infinity for all the negative numbers. So inside here, there's a plus infinity, minus infinity. And we have somehow, in this particular example, decided that that difference is going to be minus log 2.
Mm-hmm.
And you see, this is problematic, right? This is why it's trouble is around the corner.
Okay, one more question. When you were showing the harmonic series, right, the document from the internet that you found, it said that it harmonic series diverges again and again.
Can you say that one more time?
The document from online that you were showing about the first harmonic series.
Yeah. So this it is again this thing that there are professors that don't like, like our textbook. They don't like saying that you can converge to plus infinity. We call that divergence too. So for me, divergence is something that is of a different nature. Like for me, divergence is like you have this oscillation, and the oscillations, you don't get small.
Mm-hmm.
So where's my page 9 here? Where was this example? Like this one here, that one. This doesn't converge, right? It oscillates like crazy. You can easily construct other examples, like try something like, here's another example of a troublemaker, right? If I take sine of n, does he converge? Or if you want, you could take sine of, you can even make it even worse, like sine of, should be a bit more careful, right? What I want to have is sine is 0, 0. So I want to have these bubbles here. Right? So I have these bubbles. So what do I have? I have 0, and then is this pi here. Right, so if I look at pi divided by 2, I think this is right? So sine of pi over 2, this is equal to 1. And so if I move it up, like, so I'll go down here, I'll have this here will be pi divided by 2 times, what, 3? Is that right? So if I put something like sine n times pi over 2, this will oscillate between 1 and minus 1.
Mm-hmm.
So this thing in my world diverges. But in my world, I am also happy to say that this converges. But I'll always say that it converges to plus infinity.
Okay.
So if you don't like that, you can just say that this diverges, and then you can say that it diverges to plus infinity. There's just a difference between you converge to something that is just a bit outside. Like this here is not a member, right? This is not a member in R. It just converges to something that's outside R. This thing here does not converge to anything. It just keeps oscillating. So I like this much more as a label for divergence. I'm okay with converging to plus and minus infinity. There are other professors that are not, but I'm fine with this.
Mm-hmm. Okay, thank you.
Okay. Are there other questions before we wish each other a good weekend? All right. Have a good weekend, guys, and then I'll see you next week.